Okay.
Did you record the audio?
No, I did not record any audio. I think that's another room. Yeah. Okay, I'll just talk a bit louder, I guess. Yeah. Yeah, okay, let's get right into it. Why do we want to do fermionic simulation? I guess you all know this. There's lots of interesting things we can look at in quantum chemistry, condensed matter physics, which is a bit easier, where a quantum computer might work pretty well. And we've seen like a number of recent kind of proof of principle experiments. And what all of these experiments have in common is that any type of near-term demonstration is going to require the use of quantum error mitigation techniques because current systems are noisy. As a quick refresher, this is what quantum error mitigation aims to do. So we want to estimate an observable quantum error mitigation. Kind of the idea is to prepare this blue distribution, which on average is a bit closer to the ideal result. This is characterized by the bias of the error mitigation, but it comes at an exponential cost, so an increase in the variance. And this cost kind of exponentially increases depending on the amount of noise in the system and also on the error mitigation method that you're using. Additionally, all of these experiments have used some kind of symmetry verification-based error mitigation. And where do these symmetries come from? Essentially, there's two types. So we have kind of global symmetries associated typically with number conservation, spin conservation. But sometimes we can also have local symmetries, which we can use to do quantum error detection or symmetry verification by post-selection, whatever you want to call it. As an example, so this is the Jordan-Wigner encoding that we're all familiar with. I colored in some logical operators of the encoding here. And obviously the issue with the Jordan-Wigner encoding is that because it is a one-dimensional encoding, some of the logical operators, if you're trying to encode a two-dimensional system, are going to grow pretty fast. And that's why people have come up with so-called local encodings, where the weight of these logical operators stays constant as you scale up the system. And as an added bonus, what you get are these kind of local stabilizer symmetries, kind of identically as an error correction. So when we want to simulate fermionic systems, we can use out-of-the-box error mitigation solutions, but we thought, okay, let's maybe try to find something which is a bit better adapted to the problem that we're looking at. So we came up with this technique that we call substrate noise tailoring, which I want to explain very briefly right now. So essentially, this is like a very crude schematic of what a circuit looks like, and we have two types of noise. We have the undetectable noise, which does not break any symmetries, and we have detectable noise, which is symmetry breaking. And unfortunately, they do appear at the same time. So our idea was to use this error mitigation technique called probabilistic error cancellation, which can cancel any type of noise, but we only want to remove the undetectable part of the noise. Why? Because probabilistic error cancellation comes at a very, very high cost. And then we want to use essentially quantum error detection or stabilizer-based post-selection to remove the rest of the noise, because the cost associated with doing this is a bit lower. Obviously, the tricky thing here is like, how do we classify noise into detectable and undetectable errors? So essentially, we have the statement which tells you that you can essentially ignore the non-Clifford rotations in your circuit. And this is a statement which is valid also for non-Clifford circuits. I want to stress that. But what we had to resort to here is kind of the slow noise, small noise approximation. So this is kind of the main idea. Then we decided to benchmark it on some simulations. We're going to look at the trotterized time evolution of a spin 1/2 Fermi Hubbard model. And the first one we can look at is the bias of the error mitigation. So what I have here on the x-axis is kind of the circuit error rate, so how much noise we have in the system for this kind of two-dimensional distance one encoding that I was showing earlier. And obviously, the noisy results are the worst. This is the largest bias. As we add stabilizer-based post-selection, the bias decreases. Obviously, as we also verify the global symmetries via a different error mitigation technique, we gain a bit more. But if you do subspace noise tailoring, you can see that the bias is on average orders of magnitude smaller. There's one extra thing. Because we made this slow noise approximation when deriving the method, one way to kind of work around that is to do multiple parity checks within the circuit. And this kind of helps us go into this also very, very noisy regime where the circuit fidelities are, let's say, 0.1%. So this is what we would consider to be very low, even for error mitigation standards. And additionally, I wanted to mention that at a fixed kind of amount of noise in the system, at a fixed lambda, these results are kind of an upper bound for the performance that we expect for larger system as we scale up. Again, at the fixed circuit error rate. So the second thing that we wanted to look at is obviously the cost of the error mitigation. So as mentioned, this beta coefficient is what depends on the method of error mitigation that you're using. Well, lambda is kind of, as mentioned, this thing that quantifies the noisiness of the circuit. So looking at the theory, we know that this coefficient is going to depend on the weight of the logical operators of the encoding. And for local encodings where this weight is constant, then we don't expect this to really scale with the system size or with the number of trotter steps that you're doing. And it obviously also depends on the details of the native noise, how much of the noise is detectable and post-selectable at the end. So then essentially for the simulations, this is the numbers that we got. So obviously the numbers are a bit lower for higher distance encodings because they're able to detect more noise. But to kind of put these numbers into perspective, we compared them to other error mitigation techniques which are out there, which are kind of out of the box solutions that you can use, which have a known scaling in terms of beta. And here we can see that like subspace noise tailoring does outperform most of them. Symmetry verification by itself with stabilizer-based post-selection is cheaper, but it comes at a very, very high bias. So yeah, this is kind of some results from small-scale simulations of 2 sites, 4 fermionic sites. The next thing that we looked at was kind of let's try to extrapolate these results to larger system sizes. What can we learn about those? As mentioned, the cost is going to stay the same, and the bias is in small-scale simulation at a fixed noise rate is kind of just an upper bound for the performance that we expect. So just like assuming a single parity check at the end of the circuit for now, we're going to compare different encodings and different error mitigation method combinations in terms of this root mean squared error measure, which essentially depends on the bias and also on the cost of the whole method. So we gave ourselves kind of a budget in terms of the number of shots and circuits that we can execute based on this kind of recent preprint right there. And there's a couple of things that you can see right now. So for very, very high fidelities, in terms of 2-qubit gates, probabilistic error cancellation is the method of choice. The thing is that like these circuits are actually not very noisy. So this is not where we're in, this is not the regime where we're in practically. On the other hand, this kind of very noisy, also known as the realistic regime, is where symmetry verification seems to be the best choice. But if you look at the inset where you can see the value of this error, you can see that this is not, while it is the best choice, it also, the error is maybe a bit too big for this to be a practical approach. On the other hand, you can see subspace noise tailoring somewhere between 5% and 90% of circuit fidelity seem to be the method of choice. And one thing that I also want to mention here, we also try to test this with higher distance encodings, but they do not appear because essentially the extra qubits, the extra gates that you need to implement a higher distance encoding will essentially negate any benefits that you would get from being able to detect more errors. So yeah. So this was, like I said, with one single parity check, but as I've shown earlier, subspace noise tailoring can go into the very noisy regime only if we are able to perform multiple parity checks within the circuit. Obviously, there's a limit to that because we did consider noisy parity checks, but kind of trying to extrapolate now to even larger systems, we gave ourselves a budget of, let's say, 12 hours and assume that we can sample like 1,000 circuits per second. If we kind of give ourselves a 5% budget, let's say we want to be 5% accurate to estimate a single observable, then we can see, like, based on the size of the Fermi-Hubbard model and the number of trotter steps, like how far each error mitigation method, out of the 3 that we considered here in more detail, can take us. So the different colors here would correspond to different 2-qubit gate fidelity, so how good our system is, with, going from 99.9 to 99.99%. And this hatched region is what we think is kind of doable classically. Now, kind of this break-even point where a quantum computer might start to really compete against what we consider to be a very good classical algorithm kind of appears at the 6x6 lattice size and 15 trotter steps-ish. And the 2-qubit gate fidelity that you would need to get there is essentially something like 99.95%. So maybe kind of to conclude very quickly, so we do believe that this subspace noise tailoring algorithm does extend the reach of noisy hardware. Like I said, being able to go down to circuit success probabilities of 0.1% we consider to be very low. In order to really compete against classical, yes, we do need better fidelities. So these are fidelities which are still maybe an order of magnitude larger than what we can reach today. But there's additional hardware improvements that we would like to see, namely in terms of like how many circuits we are able to sample within a certain amount of time. So there's been some kind of recent improvements also in that regard. There's a couple of open questions still there. What is the optimal fermion 2-qubit encoding to use? We know that it should be low distance for error mitigation purposes at least. And it's something that should kind of map to the native connectivity of your device natively. We also know that we can improve our method a bit further. So I was showing you this kind of cost of the error mitigation, which the values that I was showing were like kind of 0.7, and we believe that there's still some room for improvement there to go down to 0.6. And obviously, any improvement in this coefficient, because it goes into an exponential, is like a very large improvement at the end of the day in terms of the cost. And we also maybe want to look at other fermionic simulation problems, maybe something like energy estimation and everything. So if you're interested in more, this is our preprint. There I have some results that I didn't have time to discuss here today, and some extra data if anybody's interested in that. So yeah, with that, I would like to thank you for your attention, and I'll be happy to answer any questions.